Okay, so last time we have introduced a probability function rho, which is defined in the phase space, and it is a function of q, p, and t, where by q, t, and p I mean the whole set of generalized coordinates for the particles belonging to our system. These are the conjugate momenta, and this is the time. Okay? And which is the interpretation of this probability? Is that it basically counts the number of possible arrangements of our system that provide that fulfill the constraints, the macroscopic constraints. So all of these points belonging to this distributed probability function basically describe the same macroscopic situation. This is more or less the idea. And all the observables are interpreted as a kind of average over this density probability. So if I have an observable f, instead of computing, let's say, the dependence of the explicit dependence of f on time, that would mean to compute how f depends on time because of the fact that f depends on all of these coordinates and momenta. We can interpret, we can compute, theoretically compute the averages by using this density probability function. Okay, and so the difference is, say that experimentally, of course, when you measure something like pressure, like every observable, it's a sort of time average in the sense that we put an instrument of measuring a measuring apparatus within our system, and we wait, say, enough time in order for the system to make the measurement, which is somehow interpreted as a sort of time average. We don't like time average because that would mean that we need to compute all the evolution of all of the particles. So then we somehow moved this dependence onto the dependence of rho in time, which of course is again a problem because we don't want to deal with quantities that depend on time. That's why we derived an equation, which is the Green equation, saying that the total derivative of rho with respect to time is a partial derivative of rho with respect to time, and as usual in analytical mechanics, I have a Poisson bracket, which is this quantity here, this is equal to 0. Okay, so now this is general, and actually this rho can actually generate also the one particle probability distribution that we introduced in the case of the Boltzmann transport equation. And the way is basically to integrate over all of the momenta and the generalized coordinates, but for one, for a specific particle. Okay, so this probability contains really a lot of information. More than what is considered, for instance, in one particle distribution of the Boltzmann transport equation. And okay, so this is not the whole story. So now we impose that when d rho dt is equal to 0, this is basically the situation in which we have thermodynamical equilibrium. So we have, we define, if you want, thermodynamical equilibrium, the situation in which rho does not depend explicitly on time. So it's a stationary function, so it's a stationary situation. Okay? And of course, now one can imagine different situations in which this guy here is not independent on time, in the sense that when this is true, That means that, first of all, when you do the average of a quantity f, you just need to do this integral. So remember now which is the notation at the triangle. T3n P and D3n Q of rho, which is a function of Q and P F divided by the same quantity that we introduced for normalization, rho of Q P. Okay, so this will be the average of a certain observable F where I do not have an explicit time dependence here. And now, of course, which is the situation in which rho is stationary? Or, well, better to say, if this is 0, then rho bracket Poisson with h must be equal to 0. And the way to realize this condition are, of course, infinite, in the sense that if I impose the thermodynamical equilibrium that the rho, the t is equal to 0, that implies that the Poisson bracket rho h is equal to 0. And then I can imagine that this situation is fulfilled whenever rho is a function of just h. Okay? So if rho is a function of h, then automatically the Poisson bracket is equal to 0. Yeah, so you know how to show this, right? I somehow someone did someone of you try to show this that this is true. Okay, non ci sono risposte.
Just use the chain rule. It's the chain rule.
Exactly, it's the chain rule. Okay, yeah, because when you do the Poisson bracket, you have to do a derivative of rho with respect to p and q, no? But you substitute the rho, the p I as the rho, dh, dpi, and similarly for q. So then, if you use the chain rule, basically you can show that this is correct. So when rho depends on h, automatically the Poisson bracket is equal to 0. Okay, but this is something that's somehow we will find later. But the basic, well, the most simple situation in which the Poisson bracket of rho with h is equal to 0 is that rho is actually a constant. Okay. So rho constant is, of course, a possibility that is somehow included in this case, and is basically corresponds to the so-called microcanonical ensemble that we have already found in the case of independent and localized systems. Okay? Now we are doing a calculation on independent but not localized systems, which is more involved. So this corresponds to the microcanonical ensemble and it's called a postulate. It's a postulate of equal a priori probability. It's called in this way: postulate of equal a priori probability. So this condition, what is saying? Is saying that basically, if we have many infinite, many ways to let's say have the same macroscopic system, and so in the same state but with different microstates, then all of these microstates have the same probability to happen. Okay, so this is basically the hypothesis of equal a priori probability. So each element of this microcanonical ensemble has the same probability to occur, and is fixed by this constant rho. Okay. Of course, now all of these all of these systems must fulfill the constraint that we have imposed at the beginning. Which are the constraints? The constraints are that they have a total volume V, total number of particles n, and the total energy, which is A. Okay, E. Sorry. Okay, so we have these constraints, which is n, total number of particles, volume, and the total energy is also fixed. Okay, so all of these elements of the ensemble are basically called usually mental copies of our system, the system we are analyzing, but with the same n, v, and e. Okay. And all of them, they have equal a priori probability. Okay, so now we have to work now with this. So first of all, remember one thing. So the trajectories, this because of the constraints, which are the constraints of total energy and total volume and total number of particles, are occupying or explore a finite portion of the phase space. I think that the phase space was called gamma. Okay. So basically, this is because the coordinates, of course, I have lower and upper limits provided by the volume, and similarly for the momenta, they can be zero, but they cannot be, say, infinitely large because I have constraints on E. So the trajectories of the particles occupy a finite portion of the total phase space. And now, if I say that rho is constant, that basically means that there is a region of gamma, of the phase space, in which rho is constant, and we will determine basically the region of the phase space in which rho is constant, and I have the constraints fulfilled. And of course, now, let's say the complementary region to this one is a region where rho is equal to 0. Okay? Okay? So when does rho is equal to 0? Well, this corresponds to the region to the points of the phase space that do not fulfill constraints. Okay? So this is the region of gamma that do not fulfill the constraints? Well, in particular, the only constraints actually that cannot be fulfilled, let's say if gamma is already, for what concern the volume, is already fixed somehow, the main constraints here that is really constraining the region in which I can have a rho constant or a rho equal to 0 is the energy constraint. Okay, so at the end of the day, it's a constraint on the energy of the single particles, if you want. Okay. Well, in principle, we know that actually the constraints of having total energy fixed would mean that my trajectories are evolving onto a hypersurface of constant energy. Okay, this is in principle my situation. Okay, I have a hypersurface, so with dimension which is 6n minus 1. And all the trajectories are moving in this onto this hypersurface. Now, actually, since we are choosing in order to do, let's say, calculations to provide a function of rho, which is a function of all the variables, and we add, and then we then add the constraints of energy. Practically, it's useful to introduce a certain uncertainty on the total energy, which is also somehow more consistent with what we do in reality. So the idea would be the following. So the trajectories move on the P equal constant hypersurface. So this is of course correct, theoretically correct, but we can assume, and this is somehow, let's say, first of all, a phenomenological assumption, and also an assumption that allows us to do, say, in a simple way, the calculation. So we can assume that actually E is determined, but with an error that I call delta. Let's say that E has an error bar. That we call delta. And actually, I do not have to assume that H of Q and P is equal to E. So we are not going to assume this. It will be the equation of the hypersurface that I was telling you before. But actually, we will assume that H of Q and P is such to be, let's say, within the error bar of the total energy E. You will understand the reason for making this assumption very, very soon. Okay? So actually, we will impose that H is not equal to E, but is equal to E plus minus delta divided by 2. Okay? So therefore now we have not a hypersurface in which my trajectories are moving, but I have a sort of let's say shell. Actually, it's a shell. It's a spherical shell in the case of non-interacting particles in the phase space, in which H is within the error bar of E, and this makes let's say allows to specify in a better way which is the rho. So now basically what happens is that rho is equal to a constant where in the region of the phase space for which H of Q and P is within the error bar delta of E, sorry, whereas rho is equal to 0 outside this region. Okay, we will figure out which is the shape of this region in a simple case, which is the case of non-interacting particles. Okay. So now we can indicate with omega, let's call it omega, the integral over all the phase space of rho, which is a function of P and Q in general, D3n, D3n Q, D3n P, which is actually equal, well, this is general, okay? And, but actually, now in this case, this is a constant within this range and is zero outside, so therefore this will be equal to a constant, which is this constant here, integral over d dn q d dn p, where h is smaller than e plus delta minus 2, delta divided by 2, and larger than e minus delta divided by 2. Okay. So now you see that apart of having this constant, which is somehow a normalization that we will fix at the end, basically what I need to do is to compute which is the region of the phase space determined by this condition. Okay? So I need to compute basically a volume. The volume. Sì?
Posso fare una domanda?
Sì.
Le variabili dell'integrale sono P e ρ o P e Q?
Q e Q. Io scrivo un po' male, scusate. Questo è Q.
Ok.
So basically,
Devo fare la domanda in inglese?
sì. Sì.
Devo rifare la domanda in inglese anche
No,
per il
non c'è
ragazzo?
bisogno. Perché c'è qualcuno che non parla italiano e non ho capito.
No, non lo so, non ho guardato, più per la registrazione.
Ma sì.
Ok.
So basically, now the calculation is basically a calculation of volume. Okay, so I need to compute the volume, the portion of volume, the volume which is a portion of gamma, in which this rho is different from 0. Okay, then I will somehow readjust the normalization, so the number of this constant now is not important, okay? So we will fix later on. Actually, it's completely irrelevant for what concerns the determination of the average values. But what is important now that I have to compute basically this volume. So a volume of the phase space which corresponds to a constraint on H, which is H within this region. Okay, that's the thing that I need to compute. Now, yeah. Once I do that, of course, now my F will be equal as before. This is the integral of d3n q and d3n p of rho, which is in general a function of p and q, but actually now this is a constant. Okay, times f of q and p divided by omega, where omega was integral, which have the same constant. So you see that the constant which is inside omega basically drops, no? So I will have integral of 3n q and p of this constant, where in the region in which h is within this region, and of course its constant drops. Okay, and similarly here, I have this integral is defined where h okay. So basically, I need to compute which is the volume where rho is different from 0, and then once I have that, I can easily compute f. Okay. Well, f in general is a function of q and p, but I have to integrate this within this volume. Okay. Good. So now the general calculation of this volume is complicated. So to compute this volume in the phase space, in general, is complicated. Especially if I have interactions between particles. For what, so in our case, we will do this calculation only in the situation in which we have free particles. Okay? So in general, the calculation of this omega is complicated, is difficult. And we will analyze the case of free particles. Free in the sense that there is no mutual interaction between the particles, but in any case they are confined in a volume V. So somehow there is an external potential that confines my particles. It will not actually take place in our calculation, will not occur in our calculation. So the Hamiltonian, in this case, in the case in which we have free particles, is provided by this function of p. We have the sum from 1 to 3n of p I squared. So this is the Hamiltonian in this situation. And vediamo come lo indico. So omega is now a constant, and let me put this constant to 1 for a moment, because it's a normalization. So it's a constant, then I have the integral of d3n q d3n p over okay. Now, of course, now I have to compute this multiple integral in d3n q and d3n p. Now, since the Hamiltonian here does not depend on q, okay, so this constraint will actually make some, is important just for the momenta. I can do already the integral over these variables, and of course what I will get is a factor of v for each of these particles. Okay, so I have a v to the power of n, which is integral over dq1, dq2, dq3 for the first particle, so then dq4, 5, 6 for the second particle, and so on and so forth. So this can be done just because the Hamiltonian does not depend on my coordinates. And then I still have to compute this integral dp1 up to dp3n in this region. Okay. Now, which is the shape of this region in the phase space Well, the shape is very simple in this case, in geometry, because the Hamiltonian is just a sum of the square of the momentum, and therefore, actually, this shape corresponds to a spherical shell. So this condition here for free particle H is a spherical shell. Okay? It's a spherical shell that I can imagine in this way. Già sotto più piccolo. Okay. So, and it is determined by an internal radius and an external radius, which are specifically E. Well, actually, it's not. Let me write it explicitly. This, sì?
Giuseppe?
Sì?
Giuseppe?
Dimmi.
Scusa, sono Michele. Non si vede un pezzo di lavagna, non so se i ragazzi te l'hanno detto, però questo cerchio che tu hai appena disegnato, se ne vede solo un
sì?
pezzo. E la H, e dalla H in poi invece non c'è scritto niente. Prova a spostare un po' la videocamera.
Ok.
In realtà io vedo tutto.
Io vedo tutto, ad esempio.
Ecco.
Dicono che vedono, non so.
Sì, adesso sì. Ok, va bene.
Vabbè. So, let me write again the Hamiltonian, which was this one. And now, of course, I have to impose that this Hamiltonian is equal to E plus delta divided by 2 and less than this quantity and larger than this quantity. Okay? So then basically, this will mean that the sum from 1 to 3n of pi squared it's it's 2m p plus delta divided by 2, and here similar 2m p minus delta divided by 2. Okay. So if you want, this is the square root of this quantity, 2m e plus delta divided by 2 is the external radius of the shell, whereas this one is the internal radius of the shell. Okay. And which is the width of this shell is delta in the energy. For what concern and the energy, the shell has a width of delta. If I want to compute the width of the shell in the momentum space, I just need to make a transformation in the sense that let me indicate with p squared. Sorry, let's indicate with p squared the sum from 1 to 3n of pi squared, and now I say that p squared is equal to 2me for the central value, let's say here, and therefore dp 2p is equal to 2m de, from which I get a relation between the width of energy, which is dE, which is equal to delta, so it's 2m delta, and the width of the momentum. No? I can simplify this one. So dP is equal to m delta divided by t. M delta divided by t. Or again can be written as m delta divided by 2me. Okay, so this is my dP. So it's proportional to the delta, so the indetermination on the energy divided by the square root of the energy. Okay, so now the thing will be to compute the volume of the spherical shell in 3m dimension. Well, actually, the situation can be simplified by considering the fact that when we have large dimension, actually the volume of the sphere and the volume of the shell are basically the same. So let's do the following calculation. Suppose that we have a sphere in a number of dimensions that I call mu, and what is the formula for the volume of this sphere in mu dimension? The volume, in general, if I suppose that the radius of the sphere is r, so r is the radius of sphere, in general would be a constant that we will determine in a moment. So to be determined. So in 3 dimensions, this would be the fourth phi. But in general, in new dimension is c times r, so the radius, to the power of mu. Okay, so similar to the case of 3 dimensions, of course. Now let me see what do I do. So suppose that now we want to compute the volume. This is of a sphere of radius r. Let's compute the volume of a sphere of radius r minus certain epsilon, which is a small quantity, and of course this will be c r minus epsilon to the power of mu. And now let us compute the volume of the spherical shell, which will be V of r minus V of r minus epsilon. And this will be equal to C times r to the power of mu, which I can collect, and then I have a 1 minus, I have this divided by r to the power of mu, so then I have a 1 minus epsilon divided by r to the power of mu. Okay? So now let's suppose that epsilon is much smaller than r, which is the fact that the width of this shell, the thickness, if you want, is much smaller than the radius. Then I can introduce the exponential and write 1 minus c divided by r is more or less equal to e to the power of minus epsilon divided by r. I'm just using a Taylor expansion of the exponential, and therefore if I introduce this, then this is equal to c r to the power of u. Then I have 1 minus, can use the exponential to the power of mu, and this is e to the minus epsilon r times mu. Okay? Now, of course, this epsilon divided by r is a small number. Okay? But actually, mu is a very large number. So let me assume for the moment that, and I will just justify this very soon. So if epsilon mu divided by r is much smaller, is much larger, sorry, epsilon mu is much larger than r, then of course this is equal to 0, and then the volume of the shell is basically equal to the volume of the sphere. Okay? Now, when this occurs, when this epsilon times mu is much larger than r. Now, is this condition somehow fulfilled? Well, consider that u is of the order of 10 to the 23, which is the number of the Avogadro number, so the number of particles that are in my sample. Okay. Well, actually, here there will be an additional factor of 3, but of course it's not important. Now, okay, so this number here is really large, and of course, even if epsilon divided by r is small, so the determination of the radius, which at the end is the determination of the energy, even if this is small, in any case, I'm multiplying this by a too much big number in such a way that actually this number here is in any case much larger than r. And therefore, I can assume that this exponential is basically equal to 0, so goes to 0 in the large n limit. Okay? So, since I have a lot of particles, so the dimension of my sphere is 10 to the 23, that basically is it's a very good assumption to make assuming so that the volume of the shell, which would be the correct volume to take into account, is actually equal to the volume of the sphere. Okay, so now in this case, my situation is even more simplified because now the integral that I have to do has just one constraint. So my omega is now this integral. Well, it has a factor of v to the power of n, which we have already said. Suppose that rho is a constant and is equal to 1, just for a moment, and we will normalize later on. Actually, we will see that the normalization must be taken with care. It's very important. And now I have this integral dp1 to dp3n, where I have a sphere of radius 2n e square root. Okay? So basically the width of the shell does not play any role. Fortunately, so that basically it's just a trick. So moving to a shell, just a trick to do the calculation, but actually at the end, even the thickness of the shell is not important since we have a very large dimension, and therefore this integral over this shell actually can be calculated as an integral of volume of the total volume of the sphere. Okay? So this was a shell. You can substitute with an integral of the volume. So now the point is to compute the volume of a sphere with a certain radius which is determined by the square root of 2me in 3m dimensions. Okay, so this will be the next task. The next task. Okay, so to do that, there is a trick. So let's compute now the sphere, the volume of a sphere of radius, come lo chiamo, R, volume of a sphere of radius R in new dimensions. And then we use this for my omega. Okay, so let's call E this integral. So this is just a mathematical bracket. So let's forget for the moment phase space and so on and so forth. Let's just focus on this geometrical problem. So to compute the volume of a sphere of radius r in new dimension. So let me introduce first this integral e to the minus x1 squared plus x2 squared plus x mu squared x1 x mu, which is a Gaussian integral that goes from minus infinity to plus infinity for all of these coordinates. And I know already how to compute this integral because each of them, so each of these is a Gaussian integral that can be factorized, no? So it's basically the integral of e to the minus x squared dx from minus infinity plus infinity to the power of mu. And of course, I know already this result, which is pi square root of pi to the power of mu. So it's pi to the power of mu divided by 2. Okay? So let's put this here and say that I is equal to pi to the power of mu divided by 2. Okay? And the integral of a Gaussian in new dimension. Okay. Now, so in general, the volume of the sphere as a function of r will be the constant that we specified before, the radius of the sphere to the power of mu, and the surface will be just the derivative of this, no? So it will be c mu r to the minus r to the power of mu minus 1. Okay, this volume in the surface. Now, the same integral I of the same function can be computed in spherical coordinates. So this integral was, let me write it again, it was e to the minus x1 squared plus x mu squared dx1 dx mu minus infinity to plus infinity. And I can write it in spherical coordinates. How? Well, I can write the integral in terms of integral from 0 to plus infinity of dr. Then I have e to the minus r squared, which comes out from this. And then I have, if you want, the Jacobian integrated over the solid angle, okay? Which in the case of three-dimensional will be a factor of 4 pi r squared, whereas in this case it will be just the surface, okay? It will be a c mu r to the power of mu minus 1. So c mu r to the power of mu minus 1. Okay. So here, somehow I have, if you want, introduced the Jacobian of the spherical coordinates, and I have integrated over the solid angle in these dimensions, this new dimensional space. And of course, now what I'm left with is just the exponential of minus radius squared times the integral of the solid angle of the Jacobian, which is basically this guy here, as in the case of three dimension. Okay. Okay, so that's fine. So let me now just, we are almost arrived at the result. So let me just do some more, so rearrange this quantity. This was I. So let me call it r squared is y, and dr, so 2r dr is dy. Therefore, dr is equal to dy divided by 2r, but 2r is the square root of y, and therefore I is equal to, when moving to these new variables, is the integral from 0 to plus infinity of dr, but dr is dy divided by 2 square root of y. Then I have a minus y here, and then I have a c mu that can be actually put aside, c mu, and then I have r to the power of mu minus 1, which is y to the power of mu minus 1 divided by 2. Okay, mu minus 1 divided by 2. Okay, this is now equal to c mu divided by 2, and integral from 0 to plus infinity of dy e to the minus y, and then I have y to the power of mu minus 2 divided by 2. Okay, by taking into account this square root. So this should be fine. And g mezzi di epsilon. Okay, so that's correct. Now, this function here actually is the Euler gamma that we had introduced a few days ago. So let us remember that gamma of z, the Euler gamma, was as this integral representation. So the exponential of minus t z to the power of t to the power of z minus 1 dt. So this was the gamma function, the Euler gamma function. And we also remember that the gamma of n plus 1 is equal to n factorial. Okay? So basically, this function here is the same as this one, but instead of having z, I have mu divided by 2. Okay? So this is the gamma of mu divided by 2. And the gamma of mu divided by 2 is actually mu divided by 2 minus 1 factorial. So this is C mu divided by 2, and then I have mu divided by 2 minus 1 factorial. Okay? And this is again the integral I. So now let us conclude this calculation that actually was done just to provide which is this constant C for the spherical for the volume of the sphere in new dimension. So I is equal to this quantity, but it is also equal to pi to the power of mu divided by 2 we derived before, and therefore I can conclude that C is is a pi to the power of mu divided by 2. Then I have mu divided by 2 times mu divided by 2 minus 1 factorial, which is mu half factorial. Okay. Okay. So this is mu half factorial. So then at the end, the volume of a sphere of radius r is this constant C that we have determined now, times r to the power of mu. R to the power of mu. Okay. So this is general. So this is the sphere volume of a sphere of radius r in new dimensions. Okay. You see now how or why the microcanonical ensemble is usually not very, let's say, it's complicated because even for the case of free particles, one has to run into this complicated volume. Well, this was easy actually, but complicated calculations of volume in phase space. So now I have this volume here, which is a general result. So let me now introduce again the omega. That was the portion of the phase space in which rho is different from 0. And we said before that this is the volume v to the power of n, which is the volume available to each of the particles. And then I have here the volume of the sphere. So let me say it here. we have volume of sphere of radius square root of q 2m times e, because this was the integral over all of the momenta from 1 to 3m of a sphere of this radius, having this radius, and in a number of dimensions, which is mu is equal to 3m dimensions. Okay, so this was the part of the integral which is relative to the integration of the momentum. So now I can use my formula that I have here and conclude that omega is v to the power of n, and then I just need to introduce this quantity here. Okay, so it's a pi to the power of mu, now is 3n, so it's 3n divided by 2, and then I have 3n divided by 2 factorial, and then I have r, which is the radius, that in my case is 2m e square root to the power of mu, which means 3n divided by 2 again. Okay. Let me check if everything is there. Yeah, everything is there. So now, but for some normalization that I will take care of later, basically this is the volume of the phase space occupied by my ensemble. Okay, is the volume of the microcanonical ensemble in the case of free particles. So free Hamiltonian. Okay. Now, so we somehow now have to remember which was the beginning of statistical mechanics, which is the fundamental equation that tells that the entropy is, but for a constant, is the constant of the Boltzmann constant, is kb times the logarithm of omega, where this was the number of microstates compatible with the constraints in thermodynamic equilibrium. Okay, so this was the formula of Boltzmann. No? Now, apart from a normalization that I will take care of in a moment, basically this omega, this capital omega and this omega here are proportional to each other. Okay. But for a normalization, since I have a logarithm, will means an additional factor. Sorry, an additive constant. No. So I can directly now compute actually the entropy in the microcanonical ensemble for the case of free particles by computing the kb, the logarithm of this quantity. Okay, And then I will take as I said before, I said now many times, we will handle the normalization in a moment. So, but let's go on and try to see what happens if I compute the logarithm of omega by remembering that as Boltzmann has assumed, the entropy is the logarithm of the total number of microstates. So Kb, so entropy now will be Kb times the logarithm of omega, which is Kb the logarithm of v to the power of n, and then okay, I have all of these factors. So pi, v, n, factorial 3 alpha n, the factorial, and then I have the energy, which is 2 m to the power of 3 n. This is the Boltzmann constant. Okay, so now, well, this is equal to Kb. Let me split the numerator and the denominator, and let me put this n, this exponent, outside from the logarithm. So I will have a Kb n, then I have a logarithm of v pi to the power of 3/2, and then I have a 2m e to the power of 3/2. So this is a quantity that I will take there, just put there. Then I have a minus kb logarithm of 3/2 n factorial, and as usual, I will use the Stirling approximation. So, okay, maybe I will write first what I get and then comment on this. So I will get a minus 3 n kb times the logarithm of 3 n, and then I have a plus 3 n kb, where I have used the Stirling approximation for this 3/2 n factorial. Okay, so I have apart from the kb which was outside, I have a 3/2 n logarithm of 3/2 n minus, but there is an overall minus because there is a denominator of 3/2 n kb. Ma c'erano delle domande? Aspettate un attimo che vedo che c'è scritto qualcosa lì. Ah no, si vede, ok, vabbè. Yeah, so this is by using the standard approximation, and so this can be arranged in the following way. So now the entropy is equal to 3/2 n kb, 3/2 n kb. Then let me put this quantity in the same logarithm. So then I have a plus nkb and diciamo di stare attenti. Ok, sì. So I have then here a volume, then I have a pi to the power of 3/2, 2 e to the power of 3/2 again, and then at the denominator I have a 3/2 to the power of 3/2, and I have a n to the power of 3/2 again. Okay, so let me check if we have all the factors there. C'è il pi, c'è il 3 mezzi e c'è quello qua di là. Ok. Let's just do some more little rearrangement of this quantity. So this is again we have NKB plus NKB times the volume. Then I have E divided by N to the power of 3/2. And then I have 2 4 terzi N pi. 4 pi
Professore,
N, sì?
non c'era il logaritmo nel passaggio sopra?
Ah, certo, sì, sì, qua. Ah, grazie.
Ok.
Sì, sì, giusto. Sì, sì. Log. Yeah, of course. Then I have, yeah, 4 third pi n to the power of 3/2. Yeah, and is the entropy. Good. So now, of course, you might remember. Well, actually, I don't know if you have seen before, but this part here is somehow something that I know already, also from, let's say, thermodynamics. This is a new part. Well, actually, let me stress that we are calculating here not a difference of entropy that one can do it also in thermodynamics, and we can do it as an exercise. But we are trying to compute, let's say, the absolute entropy. So once I have an Hamiltonian of 3 particles, I'm just asking myself which is the entropy of this system. And so basically with respect to the standard formula in thermodynamics, I will have some additional constant that actually is not important for what concerns the equation of state, for instance, but it's important for other quantities. Okay, so first of all, let me comment on this. I forgot again the logarithm. So this is NKB times the logarithm of this quantity. Okay, so let's look at this at the argument of the logarithm. There are 2 problems that one can stress. First of all, the dimension, but I will take care of this in a moment, in the sense that in principle, if I want a logarithm of something, this something must be dimensionless, of course, as every part. Okay? So I have somehow to introduce here a constant that takes care of having an high-dimensional quantity inside the logarithm. Okay, but this will manage in a moment. Actually, there is another problem which is much more severe, and this is the following. The problem is that it is the same. So it's basically due to this volume here. So here in the logarithm, I have this quantity, which is a constant, and of course it's not important. Here we have an intensive variable. So E divided by N, let me call it U, the density is an energy density, as of course it's intensity. In the sense that if I have 2 systems, and I add them together and compute, let's say, the total entropy, of course, this would be okay in the sense that for intensive variables, we know that they will not depend, of course, on the total number of particles. Okay, but the volume here is an extensive variable. So apparently, the formula that I'm getting is actually is not behaving for what concerns the extensivity of entropy. Because suppose that now I want to compute the entropy of two systems put together. So in principle, what I like to have is the entropy. It must be an extensive variable. This is one of my main, say, requirements for the entropy. It must be additional. If I have two systems with their own entropies as S1 and S2, the total entropy must be the sum of S1 and S2. And similarly, if I have two systems with volume of V1 and V2, the total volume must be the sum of V1 and V2. But actually, you see that since here I have the volume here inside the logarithm, when I add together two systems with two different volumes, the entropy will not be extensive. Okay. So since here, apart from this term here, which is clearly extensive in the sense it depends on the number of particles, has a logarithmic dependence of the volume, okay, times some factor. And of course, if I have two systems with two different volumes, I will have a logarithm of V1 plus the logarithm of V2, which becomes the logarithm of the product of V1 plus V2, which is not good. Okay. So I have a problem there, and the problem is that the fact that I have a volume here in the logarithm, which is an extensive variable, and it's written in this form, the entropy will not be extensive. Okay. So there is a problem, and here is the magic of well, if you want, it's a very important input, well, crucial input actually, from quantum mechanics that must be included even if we are considering a classical system. And so we are considering a classical system in the sense that we are working with a phase space of classical particles. So all of these particles, they have trajectories with a momentum, with generalized coordinates. There's no quantum mechanics up to this point. And what I showed to you is that if I use the Boltzmann formula for entropy, let's say in a trivial way, let's put it this way, I have a problem when computing the entropy in the sense that the entropy will not be extensive, since it has a logarithmic dependence on the volume. Now, there is a way to correct this problem. Which is the so-called correct Boltzmann counting. Boltzmann counting. Boltzmann. Which at this level, well, or if you want, at the level of Boltzmann, was just a trick, if you want. And the trick works in a magic way that I will show in a moment. But the Boltzmann counting amounts in substituting the omega that we just computed by omega divided by n factorial. So, una ricetta. No? So, at this level, this is just a trick that will solve the problem, as we will see in a moment. And the trick is that instead of computing omega, well, once I compute omega, I just need to divide omega by n factorial, where n is the number of particles. Now, of course, you know quantum mechanics, and you can justify this, and actually it is justified once we do statistical mechanics in a quantum context, quantum physics context. But the reason for this is basically the fact that in quantum mechanics, and somehow I need to introduce this very important result of quantum mechanics, that tells me that particles are identical. Okay? So then when I compute basically the phase space volume of a single particle, because at the end will be something like that, I need to correct by a factor of 1 divided by n factorial, just because all the permutations of the particles will provide the same result. So somehow, without this factor n factorial, I'm overcounting the number of available states. I have to divide by n factorial because they are degenerate, in the sense that if I change particle 1 with particle 2 or particle 3 with particle 4 and so on and so forth, I do all the permutations, the results from the observational point of view must be the same, as due to a principle of quantum mechanics that is related to the fact that identical particles indeed have such a degeneracy, in the sense that I cannot really distinguish between different particles, and then I have this degeneracy, which is basically the number of permutations. Okay, but this will come later. So the fact that this n factorial comes from quantum mechanics will come later. At this level, it's just a trick, and it's called the Boltzmann counting, that will solve anyway in a very elegant way the problem. And well, basically the trick works as follows. So when I do from omega to omega divided by n factorial, the logarithm of omega will go into the logarithm of omega minus the logarithm of n factorial, which is the logarithm of omega minus, as usual, n log n plus n, which is again log of omega minus n log n, plus, let me do this trick and write this as n log of e. Okay. So now this log of omega had outside a factor of well, n kb. Of course, I have to multiply this by kb, and then I will have an additional n at the denominator and an e at the numerator of my entropy. Okay, so when I do this substitution, the entropy will become the 3/2 n kb, which is not modified by this recipe, plus n kb. Then I have the logarithm of well, my quantity, which were b, then there was e divided by n to the power of 3/2. Then there was a 4/3 pi m to the power of 3/2. And this is what I was writing before. Giusto, no? Yeah. Now, the only difference is that when I do this Boltzmann counting, so by correcting omega with this n factorial, you see that I get a factor of n here, and then an additional E there, which is not important. Okay. Okay, so this E is not very important, it's just an additional constant. But actually, what is important is that here now in the logarithm, I have two intensive variables. So in this case, both V divided by N and E divided by N are intensive. And the only the extensive part of the entropy is just in this term and in this factor. Therefore, now the entropy is extensive. So when I compute the total entropy of let's say of two systems, I can just compute S1 plus S2. And the fact that I have two systems added together, it just basically means that here we have N1 and 1. Here I have two quantities which anyway are intensive, so they will not spoil the extensivity of S. Okay? So with the Boltzmann counting rule, basically I have managed. So Boltzmann has managed to solve the problem of the extensivity of S. That will be very important also. I'm not sure that we are going to see this today. Also for what is called the Gibbs paradox. Okay. Well, okay. So now we are happy for what concerns the fact that we have now an extensive entropy, which is due to the correction of the argument of the logarithm. Now we have to take care of another thing, which, as I said, we need to somehow readjust the dimension of the logarithm. So now we must add a constant to make the argument of the logarithm dimensionless. Okay, so I need to do some more correction. And which is the correction that I need to do? Well, basically, again, it's correcting omega. And go from the initial omega that I had, which was just the volume of the sphere associated with the momentum. Now, instead of just writing omega, I will write omega divided by n factorial, which is this correction that they have implemented already. And now, to actually have the correct dimension, I need to divide by a factor that I will write now in a way that is somehow reminiscent of something that you know, which is h to the power of 3n, where h is a constant having dimension of an action. Why I have to do this? Because when we're computing the integral over the phase space, I have the integral of several dq dp. So each one of these integral has dimension dq dp as dimension of h, of an action, sorry, of an action, right? And since I have 3n of those integrals, in order to correct them, I have to divide by h this quantity, and I have to do it 3n times. Okay? So now in this way, I will get an additional factor in this formula, which is due to this factor of h, that will provide the correct dimension to my entropy, to the formula of the entropy, which can be written now in the following way. Forse cancello anche questa. So when doing this correction, so omega that goes into omega divided by n factorial e to the power of 3n, h to the power of 3n, where h is a quantity with dimension of action, so energy times time. Then my entropy now becomes 3 half entropy plus entropy, the logarithm of v divided by n, then I have v divided by n to the power of 3 half. Sì, poi c'avevo, then I have a factor of e, and now I have a h to the power of 3, because the n is outside. Now I have a h to the power of 3n, but n is outside, and so this is h to the power of 3. Then I have 2 and 5. Let me write in this way, it will be useful later on. And these I have a 3 half, and everything to the power of 3 half. Okay. So let me see if I have everything there. So in 3 mezzi nkb, ce l'ho, nkb logaritmo, ce l'ho, ok. E questo dove ce l'ho? Okay. Okay, so this is my final formula for the entropy. I will write it in another form in a moment. That now has the property that we need to have, so that is extensive and is also written in such a way that the argument of the log is dimensionless, as it should be. You can check by yourself if you want, if this argument now has the proper, is really dimensionless, but with this we have done basically by correcting from the beginning the integrals. Okay? Now, if I want to do thermodynamics now, let me remind you that when I compute the derivative of the entropy with respect to the energy or internal energy, if you want, at fixed number of particles and fixed volume, this is my 1 divided by T in thermodynamics, okay? So this comes, if you remember, from the fact that TdS is equal to du. Okay, so here I'm treating u and d as the same way. I will comment many times on this. U is the internal energy or the total energy. These two concepts are the same in the microeconomic ensemble. So now if I do this derivative of S with respect to E at fixed volume, then of course this does not contribute. Then I have a e to the power of 3 half here, and that will go outside here. Then I will conclude that 1 divided by T is equal to 3 alpha and kb 1 divided by E. Okay? So if I compute the derivative of S with respect to E, I have a 3R NKB, then I have all this quantity here at the denominator, and then I have well, the same factor at the numerator that cancel. Okay, so then I will just add E. So this tells me that E is equal to 3R times T. Okay, and we are happy with that because actually this is the right formula that tells me something that you know already, that each degrees of freedom, and in this case we have 3n degrees of freedom, takes an energy of kBt divided by 2. Okay? So this is indeed the internal energy of a monatomic gas. Okay? So is the standard 3n, which is the number of degrees of freedom, times kBt divided by 2. Now, which is the standard result of thermodynamics? Well, we can also compute, of course, other thermodynamical quantities once we have the entropy. And for instance, we can compute the pressure by reminding that the derivative of S with respect to the volume at fixed number of particles and fixed E is equal to P pressure divided by temperature. This is the pressure. Okay. Now, to do these calculations again, now this time I make the derivative of S with respect to the volume, and the calculation follows the similar calculation that we have done before. So this guy is basically just from the logarithm I have a contribution, and will be NKB divided by the volume. Now when I compute the derivative of the logarithm. So the NKB divided by the volume is equal to P divided by T, and therefore P volume is equal to NKB T, which of course is the ideal gas law. Okay, so we also recover the ideal gas law. So we are, let's say, somehow happy in the sense that we have recovered two results from thermodynamics, this one and this one, in a fully, let's say, reductional approach, in the sense that we have started from really the dynamics of the particles, in the sense that we are taking the Hamiltonian of the particles. Okay, these are free particles, so there's just the energy is provided by just the kinetic energy. We just need to, let's say, introduce a potential that confines these particles inside a volume, and by assuming, using the formula of Boltzmann, so S is Kb times the logarithm of the number of microstates, with some corrections that we will comment later on, well, we will find again in the future, we can recover this guy here and this equation of state. Okay, so let's say that this is the the aim of statistical mechanics is basically to try to reproduce the simple example also in situations in which there is also interaction. And as you can imagine, this is very difficult in general. It's very, very difficult. Okay, But at least in this simple case, in the microcanonical ensemble, we can recover from, let's say, first principles, if you want, something that basically was just empirical in thermodynamics. Okay, so everything has been somehow reduced to the microscopic Hamiltonian of our particles. So it's a fully, we have reduced our problem fully to the microscopic properties of the particles constituting our system. Okay, so let me write again the equation for the entropy, which is the result of today. This is 3 half NKB plus NKB. Then I have the logarithm of V divided by N. Yeah, then I have E divided by N, then I have a V. And let's use the fact that E is equal to 3 half NKB T that we derived before by imposing that the derivative of the entropy with respect to the energy is 1 divided by T, 1 divided by the temperature. So let me use this result in the formula that we had before. And, well, if you do the calculations, you will end up with this, just some algebra. So if you substitute this energy there, then you will have 2m pi kBt, and I have h squared to the power of 3r. There's a bit of right? Ok, U diviso n, sì, 2n pi kb h squared. Okay. Now this equation, well, I can introduce first lambda, which is called the thermal wavelength. And lambda is by definition is h divided by the square root of 2m pi kbt. Okay, it's called thermal wavelength. And by introducing this thermal wavelength, now S is equal to 3 half NKB plus NKB, the logarithm of Bn Bne. Then I have the thermal wavelength to the power of 3 in the denominator. Lambda to the power of 3. Okay. Now this formula is called Sackur tetrode, from the name of the two guys. Yes, that Sackur tetrode equation or formula for the entropy. Okay. So this formula basically tells you that if you want to compute the entropy of an ideal gas, okay, for an ideal gas. Ideal gas in the context of statistical mechanics means free particles. So the Hamiltonian contains just the kinetic energy of the particles. There's no interaction among the particles. And this formula, of course, allows you to find the absolute entropy, if you want, of the ideal gas. And the interesting thing that this formula, even if has been derived in a context of classical mechanics, the need of correcting this formula, first of all, for what concerns the n factorial corrections, the Boltzmann counting, and the need to introduce an additional constant with dimension of action, is h, basically contains, is a classical formula, but contains or has been derived by assuming two main important ingredients of quantum mechanics, which is the fact that particles are identicals, first of all, and of course this h, now you can imagine, but h of course is the Planck constant, okay? So this formula here, of course, has been tested as a formula for the entropy, and it is correct. Okay, so we need actually to introduce this H. So one thing that I can comment more is when are we going to apply this formula, or when this formula can be actually correct? Well, this is correct. Successo? Ah, c'è un nuovo studente. So remember that, well, okay, first of all, let us see which is the interpretation now of this volume, of this, sorry, the argument of the logarithm. Well, the argument of the logarithm is b divided by n, apart from this e, which is not important for what I'm saying. And then I have an additional 1 divided by lambda cube. Now, if you want, this is the volume available per particle. So if you want, this is called also specific volume, which is the inverse of the density. And the specific volume is divided by the lambda, which is, well, lambda cubed. So if you want, I have the ratio of two sides. One is the, let's say, the linear scale of my macroscopic system, which is L, divided by the number of particles. So is the, if you want, is the well, is the volume available for the particle, or in terms of a length scale, is a length scale divided by the number of particles characterizing my macroscopic system, divided by a length scale lambda, which contains quantum mechanics. The length scale lambda is a thermal wavelength, and it is basically the generalization of the de Broglie wavelength in the case in which I have a gas of particles with a certain temperature, which is here. So then I expect my approximation, so the fact that I have neglected actually quantum mechanics, because I have treated my system in a classical way, apart from correcting maybe some correction, this formula, the Sapor is correct when the lambda is very, well, when this, so the lambda is very small in comparison with this b divided by n, basically, okay? So when basically I have to assume, in order to find the, scusate ma questo rumore è terribile, voi non lo sentite ma io lo sento pienamente, difficile concentrarsi. Okay, so the classical limit, which also is basically the proper limit for this equation. I have to impose that questo n lambda cubo divided by the volume is much smaller than 1. Which means that, let me see again. So I need to impose, yeah, okay, this is much larger than 1 if you want. Okay, in this case, I'm saying that the volume available for a single particle is much larger than the volume provided by the thermal wavelength to the power of 3. Okay, so somehow in this condition, I'm not seeing the fact that the particle has a wavelength, so as a quantum nature. Okay, so the validity of this formula, which is a classical formula, although it contains some ingredients of quantum mechanics, is the argument of the logarithm is much larger than 1. That means that n lambda cubed divided by the volume much smaller than 1, which is realized when this happens, so that the lambda is large, and to have, lambda must be small, which means large temperatures. Because for large temperatures, lambda, which scales as the square root of 1 over t, will be small, and small densities. So n divided by d, which is small. So the equation for the entropy that we have derived, as I said before, although it contains some quantum mechanics ingredients, it has been derived in classical mechanics, and its range of validity now can be set by just comparing the specific volume and the volume provided by the thermal wavelength. And we find something that we expect indeed, namely the fact that this approximation is correct when the density of particles is small, and you remember, of course, that when having an ideal gas, a crucial assumption that is done is that you have a low value of the density of particles in such a way that the interactions can be neglected. And the other thing which is very important is the large temperature limits. So the lambda must be small, which means large temperatures, and indeed the classical statistical mechanics is correct for large temperatures. When we go to lower temperatures, to low temperatures, the corrections due to quantum mechanics start to become important, and we need to take care of these corrections. And the sample-tapered formula that I've written before is not valid anymore. Io direi di chiudere perché ho già sforato, che sono già le 11. Una domanda. Allora, io, diciamo, facendo estrapolazione delle ore, a me sembra che diciamo, tenderemmo addirittura a sforare oltre la metà di giugno. Quindi non so adesso se possiamo recuperare in qualche modo le ore fissando qualche altro orario, oppure se possiamo eventualmente prolungare, ad esempio, le 2 ore del martedì, fare invece che 2 ore, fare 2 ore e mezza. In linea di principio, però devo chiedere, per voi potrebbe essere un'idea? Cioè, di invece... Sì, dimmi.
Io sarei tra le due, preferirei fare più piuttosto che prolungare quelle precedenti, poi non so gli altri. Però sì, per me sarebbe fattibile, non c'è problema.
Cioè, se riusciamo a fare una mezz'oretta in più, scusa Luciano, adesso chiudo, ho finito, stavo solo chiedendo una cosa. Se riuscissimo a fare una mezz'oretta in più il martedì, perché il martedì noi siamo dalle 11 all'1, potremmo fare invece che dall'11 all'1, dalle 11 all'1 e mezza, in questo modo recuperiamo ogni settimana mezz'ora e adesso non ho fatto i conti, però sicuramente ci potrebbe aiutare un po'. Quindi eventualmente, però devo chiedere, per voi potrebbe andare bene se facciamo mezz'ora in più il martedì?
Se invece facciamo delle lezioni aggiuntive, quante dovremmo farne?
Non lo so, guarda, se volete fatevi i conti anche voi. Noi, diciamo, il corso, diciamo che ha una durata di 54 ore, credo. Però abbiamo cominciato 2 settimane dopo.
Sì, ok.
E inoltre, in questo periodo ci sono molte vacanze,
Ah.
perché anche la settimana prossima ci sono le vacanze di San Giorgio, poi c'è il ponte forse del 1° maggio, ma quello forse non riguarda questo corso. Però di sicuro la settimana prossima c'è, credo, un'ora che saltiamo, se non sbaglio, che è proprio il giorno di giovedì, che è il 23. Quindi, allora, facciamo così, pensateci anche voi. Io chiedo anche al nostro coordinatore del corso di laurea, perché non sono neanche sicuro che dobbiamo recuperare le ore avendo cominciato 2 settimane dopo, oppure se, diciamo, dobbiamo tagliare il programma. Cioè, non voglio prendere iniziative senza chiedere a lui prima. In linea di principio, se per voi va bene, io sarei ad esempio disponibile a fare mezz'ora in più il martedì, che così guadagniamo ogni settimana mezz'ora e questo sicuramente ci potrebbe aiutare. Comunque consultatevi tra di voi, io poi chiedo al coordinatore del corso di laurea, va bene?
Va bene.
Va bene.
Arrivederci.
Va bene, ok.
Scusa Luciano, chiudo subito. Ciao.
Arrivederci.
Arrivederci.
Allora, chiudo la registrazione.